In this lesson, we discuss lazy learning. We will go over lazy learning, the famous nearest neighbor-based prediction, and discuss challenges and solutions. So far, we built classifiers, trained them with examples, and used them to make predictions. This is the eager approach. On the other hand, the lazy approach involves storing the data in an appropriate form and deferring a classification until a prediction time. Lazy learning benefits from incremental learning, but this is going to come at a cost. In the k-nearest neighbor, we are trying to classify a query point based on the neighborhood around it. And in this illustration, we have a data set with two classes. Let's say the circles are the plus and the x's are the minus. The question marks are the query points. So the KNN algorithm works by looking at the class label of the nearest neighbors. So let's say in this case we have 1, 2, 3, 4, 5 for k equal 5. It's going to look at the weights and the class label of the k neighbors. In this equation, as you can see, yq hat equals the sum of the neighbors' weight multiplied by the class label divided by the sum of the weights. And this weight can be something simple as 1, or it can be a very complex similarity function. And as we all expect, a lazy learning algorithm like KNN relies a lot on a proper indexing, maybe hashing, because the data management and the storage are very crucial to support incremental learning, which is very computationally expensive. In terms of accuracy, lazy methods use a richer hypothesis space because they rely on so many local linear functions. So these functions form an implicit global approximation to the target function. In other words, rather than trying to create a single model that fits the entire dataset, lazy methods make predictions based on localized patterns within the data. On the other hand, eager methods need to commit to a single hypothesis that covers the entire space. So in other words, they try to fit a global model to the data up front, and they make general prediction across the entire dataset without the benefit of these localized adjustments or patterns. There are several sub-problems that follow lazy learning or KNN approach. For instance, a common distance metric used in KNN is the Euclidean distance, but there are also other ways to measure the similarity between the neighbors. So one way is to use locally weighted regression. For example, we may construct a local linear model that fits the data within the neighborhood. So we essentially fit a linear model, but only for the local context. And of course, this can be extended to more complex machine learning functions that learn from the neighborhood and use that for classification. Another extreme is called case-based reasoning, where whenever you face a new problem, you refer it to a database or a repository of past cases. Implementing k-nearest neighbor has a lot to do with how to define the distance metric. Is the distance between the points treated equally, or maybe different weights depending on how close or far these points from the query point? And once we figure out the distance, now we start to think about how to normalize features. And as always, they're going to be more than one case. Is the data numeric or nominal? So the approach is going to be different depending whether we're dealing with continuous numeric data or categorical values. To summarize, we have data points and a test point representing the query, for which we need to make a prediction. This prediction can be based on the weighted sum of the nearest neighbors. Sometimes it can be done through simple majority vote. Sometimes we need to handle data quality issues, but one of the important questions, how to choose k. So is k going to be a small number or a large number? So for small k, now we are dealing with small communities, and the class labels are going to be mixed inside these localized communities. But if the value of k is a large number, that means we have a larger region of points, and eventually we can expect that the majority class will dominate, leading to somehow of a uniform classification. And as we mentioned, the data points are n-dimensional. We use a form of distance function, and depending on whether it's a classification or a prediction, we can have a class label or a value that represent the prediction. Another interesting method for implementing k-nearest neighbor is using the Voronoi diagram. If you ever studied Voronoi diagram in geometry, you might recognize that it splits the space into regions. So if you take two data points, this line in the middle split the space between the two data points. So if there is a query point inside a cell, then the point inside the cell is closer to that point. It's an interesting geometric variation of the k-nearest neighbor. More discussions. So when using KNN for prediction, we can take the mean values of the k-nearest neighbors. And when we talk about distance-weighted nearest neighbor algorithm, we typically define the weight in a way that gives a greater weight to closer neighbors. That's why you see weight definitions in the form of 1 over d or even 1 over d squared. KNN is robust to noisy data by averaging the k-nearest neighbors. To overcome the curse of dimensionality, we can do a form of dimensionality reduction by eliminating the least relevant attributes. This is a great visualization to show how different values of k lead to different solutions. So when k is very small, you're going to see small communities or islands. In these cases, data points from one class in neighborhood may dominate, causing those clusters. So, for example, we might have a large green region, but inside this large green regions, we have some reds that made an island. And this can sometimes lead to overfitting as the model starts to focus on noise or even irrelevant data. On the other hand, when increasing the value of k, here k equals to 117, you can see how the majority class will eventually dominate. So the choice of k nearest neighbor has received a lot of attention in literature, and there are so many papers on this topic. Some of the challenges encountered in implementing k nearest neighbor algorithms: getting the distance function right, and it depends a lot on the data set. So a distance function needs to learn parametric distances dependent on the data, deal with data quality issues, optimizing computations by using parallel computing and efficient data structures, more on speeding up computations using partial distance calculations, editing, compression, and using hashing techniques like locality-sensitive hashing. In summary, we discussed lazy learning. Specifically, we talked about the nearest neighbor-based prediction, discussed challenges and solutions.